We've looked at the area under a curve. That's what we just did in section A. But now we want to look at kind of an extension of that idea and find the area between two curves. Okay? This is kind of an interesting concept here. You see these two functions, f of x and g of x. All right. Here you have f of x that looks like it's probably some kind of a parabola or something. And then you have g of x that looks, I don't know, maybe that's a logarithmic function or something like that. Okay. But they have these intersection points, and what we want to find is, hey, what's the area contained inside, in between these two functions? Okay? It's kind of an interesting look because what this ends up giving us is, kind of this odd looking shape, all right, but we're able to find the area of this odd looking shape. And what's cool about it is, after we look at some kinematics applications, another application we're going to look at is what's known as a solid of revolution. Okay, finding a volume. And what we actually do is we can take a shape like this and then spin it around the x-axis. And make a three-dimensional object that kind of has, in this case it would have a hole inside of it or whatever. But we could spin it around and we could figure out what the volume of that thing was.
The one that looks like a square root function, is that G or F?
This one is F. This one was G. Okay? So notice here,
area. Everything under F?
If we want the area of this shaded region, look at the integral that we're going to use. We're going to do the integral from A to b of the f of x minus the integral from a to b of the g of x. Okay? Now, I want you to see what's going on here, because what happens is when I find the integral from a to b of the f of x plus k, look at the area I'm actually getting. I'm actually getting all of this area right here. Right? Because it's between the x-axis and my function f. Alright?
And then you're taking out the g part.
Exactly. The area, that second integral with g of x, is the stuff that's below g. So I'm subtracting the part that I don't want, and that's how we end up with just this part that we do want. Does that make sense? Okay? Now, we can simplify this rather than doing two separate integrals. We can simplify this into the integral from a to b of f of x minus g of x. And this goes back to our properties of integrals. If you remember, when we had an integral with the same interval, a to b, and it was added or subtracted, we could combine it into one integral, or we could separate it into multiple integrals, whatever was most useful. In this case, we're combining these into two integrals into one, the integral from a to b of f of x plus k minus the g of x plus k. Okay? And notice here, a k minus a k, those k's cancel out, and I just have f of x minus g of x. Alright? So that's how we get this formula. Alright, so this is a formula you should be familiar with. Okay? The integral from a to b of the difference. Now, I want you guys to try to come up with how we're going to determine what A and B are and what f of x and g of x are. Okay? First of all, what are A and B?
The two endpoints, the x-axis of the term, where the intersection.
Okay, good. They're the intersection points of my two functions. They're the endpoints of this region that I'm trying to find, but this region is defined by intersection
Yeah,
points.
because if it's not an intersection, there's gonna be other areas
Hey.
on the left.
Yeah, and actually that brings up another issue here. If we had a function that like came back like this, and this one came back like this,
Yeah.
you might have another interval that you would need to find the area of, and we would add it, okay? However, if that were the case, and we'll look at an example like this, we would need to be careful because, here's my follow-up question to the first one. How do I know it's f of x minus g of x, and not g of x minus f of x?
That's why I asked you which one is F, because I thought this one was F, so you wouldn't make sense. Like
Yeah.
The one that's above is what
Well,
you
it's going
subtract
to-
from.
The one that's concave.
That's right. The one that's above is the one that you're going to have, and the one that's below you're going to be subtracting. Okay? You want to subtract the area below the bottom one from the area under the top one.
So like
Okay.
you do concave down minus concave up.
If it helps to think of it that way, that's not technically correct. Because, I mean, we could have, here's the thing, we could have two parabolas and they're both concave up.
Oh, okay.
You could have something like that, and we're finding this area here.
So what would be f of x and g of x?
Just think of which one is on top
Okay.
inside the interval. Whichever one is on top, that's going to be your f of x. The one that's below is the one you're subtracting. Okay? So, kind of to give ourselves a little bit of a procedure here. First of all, we've got to determine the interval by finding intersections of the curves. Okay? So if we were actually doing this problem, we would have to figure out, hey, what is A and what is B? What are those intersection points? Secondly, in those intervals, which function is greater? Which one's on top, like we just said? Then, integrate the difference as seen above. Okay? Integrate the difference here that we find. Okay? What you'll find with these is that sometimes it actually gives you a very simple function to integrate because you're subtracting and things might cancel out or whatever. Okay? So let's look at an example and kind of run through this whole process.
What was the third step? Because I was copying.
Just use the formula basically. Plug it into the formula and use the formula. Okay? And again, the key here is f of x is greater than g of x for all x's inside the interval from a to b. And I guess you could put greater than or equal to, but okay. So let's look at this one. We'll start out simple where we don't have to necessarily find those intersection points, we just have to see them, okay? But notice here, I want to find,
So confused.
oh, you don't have class.
Apparently, like I had class at the end of this period, where she told us that. I'm just gonna
Is it
say
5B
Okay.
for the right?
5B, yeah.
Yeah, you have to. It starts at like 12:40 and then it ends at 1:20.
12:40. So it already started.
Yeah, you just.
I went there and no one was there. They said that they leave their class at 1 when this class ends.
Oh, wow.
No
Okay.
way.
Yeah, no way.
I don't know.
Me and her used to leave at like 12:30.
So
Oh.
For her
I'm
class.
sure we'll get it worked out. Alright, so with this one, we have this line and we have the parabola. Now they gave us a nice picture already So we can see that the intersection points are at -2 and +2. So when we integrate, we're going to be integrating from -2 to +2. Now, if we weren't given this, we would need to actually calculate where these intersect. How would we do that?
Find the zeros.
Critical value.
I mean, you could draw, like graph it. I mean, it's not too hard to graph a parabola.
No. But how do we find where two things intersect?
Make
Can you make them
equal to each
equal?
other.
There we go. Make them equal to each other. X plus 2 equals x squared plus x minus 2. So we get it equal to 0 since it's a quadratic. You get x squared. X minus x is 0. -2 minus 2 is a -4. And you get x equals plus or minus 2. Okay? So there's our intersection points. If they're not given to us, we can find them. Okay? Now, so that was step 1, figure out the intersection points. Where are we going to be integrating? If we got more than 2, then we would need to separate it into 2 different integrals. Okay? We'll look at one like that in our next example. But here, since we only have 2, we're going to have one interval that these are that defines this region between them. Okay? Which function is on top?
X plus 2.
The x plus 2. Alright, so we're going to take the integral, okay, this one's on top, we're going to take the integral of x plus 2 minus the bottom function. The bottom function is the parabola, x squared plus x minus 2. Okay? Now, simplify first. Integral from -2 to 2 of, we have a negative x squared. We have x minus an x, so that's gone. We have 2 minus a -2, so that's plus 4. Okay? So now, what's the integral of negative x squared?
X cubed over 3
Very good. Negative x cubed over 3.
plus 4x.
Good. Plus 4x. Evaluate that from -2 to +2. And this is going to give our area between the line and the parabola. Okay? So if I evaluate it at +2, I have a -2 cubed over 3 plus 4 times 2 minus a -2 cubed over 3 plus 4 times -2. Okay. Lots of negatives to be careful with here. Alright. So we've got a -8/3 plus 8 minus, this is going to be a +8. Because -2 cubed is -8 times a -1 is +8/3. So minus that. Then this is a -8. So minus a -8 is +8. Okay? So we add all this up. We have 16 and minus 16/3, which is 5 1/3. Okay? 16 minus 5 1/3 is 10 2/3. So that's our area.
There's 3 minuses.
Yeah. This was cubed, so it stayed negative, then it was made positive, but then that made it negative. So. Alright, does that make sense? Alright, let's try one more. We'll end with this one. Okay. Here it says, find the total area of the regions contained by y equals f of x and the x-axis for f of x equals x cubed plus 2x squared minus 3x. The x-axis is simply y equals 0, right?
Mhm.
Now, check this out. I have 3 intersection points with x cubed plus 2x squared minus 3x and 0. Okay? I am intersecting the line y equals 0 with my function, in other words, finding the zeros. If I were to factor this, I'd get x times x plus 3 times x minus 1, and I get those intersection points to be 0, -3, and 1. Okay? Now, we need to be careful that we put them in order smallest to largest, because here's what I'm going to do. I'm going to take the integral from the furthest left point, -3, up to 0,
And 0.
and then I'm going to add the integral from 0 to 1. Okay? So, for each interval, I need to tell which one's on top and which one's on bottom. So, in this interval, obviously the x cubed one is on the top. So, I have x cubed plus 2x squared minus 3x minus 0 dx. Alright? However, for this one, the line y equals 0 is on top. So check this out. I've got 0 minus x cubed plus 2x squared minus 3x dx. Okay? Now you might remember we said one way you can handle this area below is to just add the absolute value. Or, notice in this case what happens, it's times the -1. Okay?
So it's just.
So if it's under the thing, you have to switch the order.
If it's under, you always do the top one minus whichever one's on bottom. Okay? So if we were to simplify this here, we have the integral from -3 to 0 of just the x cubed plus 2x squared minus 3x dx. And then 0 minus this. I have now plus the integral from 0 to 1 of -x cubed minus 2x squared plus 3x dx. Okay? And you have the option. You could either distribute the negative like I did, or you could have left this and pulled the negative out in front of the integral since it's a constant multiple. Alright? But now we have to integrate both of them and add the areas together. So, x to the 4th over 4 plus 2x cubed over 3 minus 3x squared over 2. That whole thing is evaluated from -3 up to 0. But then I need to add to it. I'm going to do it on a separate line so I don't get confused here. We have a negative x to the 4th over 4 minus 2x cubed over 3 plus 3x squared over 2. That's evaluated from 0 up to 1. Okay? Now, when I plug in 0 in both of those, it's 0. So, I need to plug in a -3. So, -3, and it's going to be 0 minus all of this. -3 to the 4th over 4 plus 2 times -3 to the 3rd over 3 minus 3 times negative 3 squared over 2. Alright? So this is a negative 81 over 4 minus, because that's a negative 27, so that's a negative 54 over 3. And then that's a positive 9, so minus 27 over 2. Okay? I've got to add that to this, evaluated from 0 to 1. So it's going to be it evaluated at 1, so negative 1 to the 4th over 4 minus 2 times 1 cubed over 3 plus 3 times 1 squared over 2, and then minus this evaluated at 0, which we said was 0. Okay? So this whole thing is a negative 1/4 minus 2/3 plus 3/2. And now we can add these together to get our final answer. Okay? So the area is negative 81/4 plus 54/3 plus 27/2 minus 1/4 minus 2/3 plus 3/2. And you can figure out what all that equals. Negative 82/4. That's going to be plus 52/3 plus 30/2. Okay. This is negative 41/2. Plus 30/2 is going to be a negative 11/2. Plus 52/3 is 17 1/3. So I have a negative 5.5 plus 17 1/3. So that's going to be 11 5/6. Okay, so that's our total area contained between those two curves.
You just put it in units, right? It would just be in units.
Yeah, square units or whatever is fine. Okay? Now, if you happen to look at the PDF, there are problems. We are not doing that for IP because you have your problems that are already due on Thursday. Thursday, we're going to take the time to practice this concept. Okay? So don't do that independent practice between now and Thursday.